Alright, 3.60 number 2, we're going to talk a little bit more about position, velocity, acceleration. So I'm going to go off camera for a moment and work through a few items here with parts A through D. Okay, so you can see here velocity function would be the derivative of the position function given in part A, and part B would be the second derivative of the position function, which would be the derivative of the velocity function, which is the acceleration function. So here in part C, I set the velocity function equal to 0. That's going to help me to test some intervals in a moment. Once I know where the velocity equals 0, then I can test around that and find out where the velocity would be negative or positive, which would then determine whether or not it's moving to the left or to the right. Okay, so now I've got a nice, I got a little interval testing device here that I've got going on. So I'm going to test values between 0 and 1, 1 and 3, and then something greater than 3. And I'm going to determine then where the velocity is positive or negative. I already know at these 2 points at 1 and 3 it's 0, so I'm going to test around it. So if I were to test it, a couple different ways you could do this. You could plug a value in, right? V of, let's say, 1/2. Right, that's going to come out to be positive. I know that because this parabola here opens upward. So I know those values there will be positive between 0 and 1. If I were to test then a value between 1 and 3, like say 2, I know that's going to be less than 0, and then again it'll duplicate more positive values to the right. So I know then that the particle is moving to the left when t is between 1 and 3, and the particle is moving to the right when t is between 0 and 1 or greater than 3. And I know that because the sign of the velocity function is positive on the intervals where it's moving to the right and negative on the interval where it's moving to the left. So let's talk about when would the particle be speeding up. So with regards to speeding up, what I'm going to want to do is I'm going to want to compare the velocity outputs with the acceleration outputs. So the first thing I want to do is find out where the acceleration is going to equal 0. So I'm going to take the acceleration function, which is 6t minus 12, set it equal to 0, and solve. It looks like acceleration will equal 0 at t equals 2. Okay, and if I were to test values on either side of that, acceleration will be negative when x is between, or t is between 0 and 2, and it will be positive when t is greater than 2. So with regards to acceleration, we know this would be concave down, and this section would be concave up. Now when we compare these, let's talk speeding up, slowing down for a moment. So the particle will be speeding up when the signs are the same. Okay, when the signs are the same. So I'm going to compare these two diagrams. And what you're going to see is that here, the signs are going to be the same. Right? And also here. So the particle is going to be speeding up on that interval. That interval would be from 1 to 3, from 1 to 2, as well as from 3 to infinity. Therefore, they would be slowing down when their signs are opposite. So they would be slowing down when their signs are opposite. So the particle will be slowing down on the interval from 0 to 1 and from 2 to 3. Alright, so we're not going to make a t-table in part E. We're just going to move on to our next topic here. let's draw a schematic of the position of the particle at time t. Okay, so I took the position function here, s of t, and I plugged in 0, 1, and 3. You start at 0, we had a change in direction at 1, and another change in direction at 3. So from time t equals 0, where we were located at 0, time t is 1, we're located at 4. Time t equals 3, we were back at 0. And then indefinitely we would be moving to the right. So it looks like we move right, then left, then right indefinitely. So that would be, and you could put, directionally where the particle is moving, but that would be a schematic of the position of particle at time t. Okay, so here we are on AP Example 2010. No calculator allowed. A squirrel starts at a building A at time t equals 0 and travels along a straight horizontal wire connecting building B. For the times 0 to 18, the squirrel's velocity is modeled by the piecewise linear function defined. At what times in the interval does the squirrel change direction, and give a reason for your answer? So just looking at this, I would look to see where the velocity changes from positive to negative or the other way around. So I see at time t equals 9, and I also see at time t equals 15. Since velocity's sign changes at both of these points, then there's a change in direction. Okay, so we could say that since velocity sign changes, there's a change in direction. Part D says to write expressions for the squirrel's acceleration, velocity, and distance. I'm going to scratch the distance for a moment and just do acceleration and velocity. So if I look at this window here from 7 to 10, that can be represented using a linear function. Now the slope or the derivative of the velocity function would be the acceleration. So the slope of that line, of course, would be constant, and so the acceleration between times 7 and 10 looks like would be the slope or the velocity's derivative, which would be y minus y to negative 10 over x minus x. That comes out to be 30 over negative 3, which is negative 10. So during this interval, the acceleration would be negative 10. Meanwhile, the velocity expression or equation during this interval could be represented using the equation of that line. And so just looking at point slope form, if I have a coordinate and a slope, I can write the equation of this line. I already know the slope of that line is negative 10, and I know one point for sure is the point 90. And so if I distribute, looks like I'd get y equals negative 10x plus 90. That would be my velocity equation for that time interval. I know I'm using t as my independent variable, so I used x over there for a moment, but I'm going to swap back, and that would be my velocity expression for that time from 7 to 10. Okay, last example for today. It says a particle moves along the x-axis so that its position at any time t is greater than or equal to 0 is given by that function. The particle is at rest at what time for t? So I'm going to take x of t, and I'm going to find its derivative, which is going to require me to use the product rule. So I'm going to go off camera for a moment and come back with an answer. Okay, so I used the product rule, derivative of the first times the second, plus the derivative of the second times the first. Be careful with that e to the negative t. And then I did something kind of interesting here and factored out an e to the negative t. And the reason why is because this right here, this expression can never equal 0. It never will. So if I want to know where this particle is at rest, I want to know where the derivative equals 0, which clearly this cannot ever equal 0. So all I want to know is when this could equal 0. So 2 minus 2t would equal 0 when t equals 1. So it looks like C is our answer. The particle will be at rest at time t equals 1. Alright, so that's 3.6, day number 2 in the books. See you next episode.